Welcome to the lecture series of signal system. In the previous lecture, we have seen some basic properties of the Fourier series like time shifting, linearity, time reversal and time scaling. In the linearity, we have seen that if a signal x1t produces the Fourier coefficient Cn and x2t produces dn, then ax1t plus bx2t will produce acn plus bdn. This property is called linearity property of the Fourier series. Next, the other property was if a signal xt produces the Fourier coefficient Cn, then x of t minus t naught will produce the Fourier coefficient Cn multiplied by e power minus jn omega naught t naught. The Fourier coefficient Cn will be multiplied by e power minus jn omega naught t naught, where when the shift of t naught is given to the signal xt, this property is called time shift property of the Fourier series. Now the another property was time reversal property, in which we have seen that in the time reversal property we have seen that if a signal xt produces Fourier coefficient Cn, then x of minus t will produce c sub minus n. This property is called time reversal property of the Fourier series. Another property what we have seen in the previous lecture is time scaling property, which states that if xt produces a Fourier coefficient Cn, then x of alpha t will also produce the same coefficient Cn, but omega naught in the relation of Fourier series will be replaced by the constant alpha, the scaling factor alpha into omega naught. Means xt, now xt will be expressed as n is from minus infinite to plus infinite Cn e to the power j n alpha omega naught into t, jn alpha omega naught into t. It means that if the signal which Fourier transform we have to obtain is multiplied by a constant alpha, here it is x of alpha t. If the signal xt is scaled by a factor alpha, then the Fourier transform of x of alpha t, Cn will remain same, but the e power omega naught will be replaced by alpha times omega naught. This property is called time scaling property of the Fourier series. Now there are some more important and useful properties of the Fourier series. We will come to know in few minutes. The next property is time differentiation property of the Fourier series. This property states that if xt produces a Fourier constant Cn, then dy in the Fourier series of d by dt of xt, the Cn will be replaced by Jn omega naught into Cn. Means Cn will be multiplied by a factor Jn omega naught. Here is the proof. We know from the from the definition of Fourier series, xt can be represented as xt is equal to Cn sigma n is from minus infinite to plus infinite Cn e power j n omega naught t. Now, if we differentiate both sides of this equation with respect to t, we will get dxt over dt is equal to sigma Cn d by dt differentiation of e power j n omega naught t, and differentiation of e power j n omega naught t will be equal to j n omega naught into e power j n omega naught t. So the term e power j n omega naught t will be replaced by this term after differentiation. Then the equation will become Cn into this will become dy dt of xt is equal to sigma n is from minus infinite to plus infinite jn omega naught Cn into e power jn omega naught into t. On comparing with the standard equation of Fourier series, we will look in this equation, we will get that Cn now is replaced by Jn omega naught into Cn. It means that the given relation will become, when we will differentiate the signal xt in the Fourier series domain, the Cn will be replaced by Jn omega naught into Cn. Now similarly, there is another property which is called time integration property of the Fourier series. In the time integration property of the Fourier series, we will see that if a signal xt time integration, this is time integration property which states that if the signal xt produces coefficient Cn, then integration from minus infinite to t x tau d tau will produce Cn upon Jn omega naught, where C naught is equal to 0. We will look this property in the next coming slide. Time integration property, which states that xn xt produces Cn, then a different integration of xt d tau x tau d tau will produce Cn over Jn omega naught if C naught is equal to 0. Means initial conditions are 0. So here is the proof. By the definition of Fourier series, we know that a signal xt can be expressed in the complex exponential form as xt is equal to sigma n is from minus infinite to plus infinite Cn e power jn omega naught t. If we will integrate both sides of this equation with respect to tau, where limit is from minus infinite to t, then its left side of the equation will become integration of x tau d tau, where limit is from minus infinite to t, and right side will become sigma n is from minus infinite to plus infinite Cn integration of e power jn omega naught tau d tau. Here this variable is tau, this is a dummy variable finally we will get result in the form of t. So the differentiation of integration of e power j n omega naught tau will be equal to e power j n omega naught tau over j n omega naught. After putting this value in the equation, we will get here that the upper limit of the integration is t, while the lower limit is minus infinite. When we will put upper limit minus lower limit, this will become e power j n omega naught t over j n omega naught minus e power minus infinite upon j n omega naught. This e power minus infinite can be written as 1 over e power infinite, which will lead to 0. So this integration will become Cn, n is from minus infinite to plus infinite, Cn over Jn omega naught e power Jn omega naught t. It means that if we will compare with the representation of xt in the form of complex exponential Fourier series, we will get in place of Cn there is another term Cn upon Jn omega naught t. It means that if we will integrate the signal xt from minus infinite to t, then the Cn will be divided by Jn omega naught. This property is called integration property of the Fourier series. There are some other important properties. The convolution property or convolution theorem, very important property, in which this property indicates that if x1 produces a coefficient Cn and x2t produces a coefficient dn, then x1t convolution x2t, when we will write the Fourier series of this convolution x1t convolution x2t, it will produce the coefficient t times Cn into dn, where t is the fundamental time period of the given signal. It means that if we will multiply the signal, if we will take convolution of the signals, then their Fourier coefficients will be multiplied. This is the convolution property. Now we will see the proof of this property. We know that the Fourier coefficients of a signal can be written as integration 1 upon t integration 0 to t xt e power minus j n omega naught t dt. Here in place of xt, the given signal is x1t convolution x2t. In place of xt, we will write here x1t convolution with x2t. So this relation will become this relation will become 1 upon t integration from 0 to t x1t convolution with x2t e power j n omega naught t dt. And we know that the convolution of two signals x1t and x2t can be written either as integration from 0 to t x1 tau x2 t minus tau d tau, or it can also be written as integration from 0 to t x1 t minus tau x2 tau d tau. d tau. So in place of x1t convolution with x2t, we will write this expression. So the relation will look like, when we will put the formula of convolution, the relation will look like integration from 0 to t x1 tau x2 t minus tau d tau e power minus j n omega naught t dt. Now here it is x2 t minus tau. Now we will replace this variable with a dummy variable t dash, means we will put t minus tau is equal to t dash, then dt will become dt dash, and in place of t, here the limit will become, when t is equal to 0, then t dash will become minus tau, and when t is equal to capital T, then t dash will become capital T minus tau. So the limit will be from minus tau to t minus tau. Then this integration will look like integration from 0 to t x2 x1 tau x2 t dash e power minus j n omega naught, because we have written here t minus tau is equal to t dash, then here the t will become tau plus t dash. This t will become tau plus t dash, that is written here. Now we will change the order of integration and break e power minus j n omega naught t dash plus tau as given here. We will write e power, this term we will write as e power minus j n omega naught t dash into e power minus j n omega naught tau. Now we will put this e power minus j n omega naught tau with this integration, and e power minus j n omega naught t dash with this integration, and this integration will become here, this e power minus j n omega naught tau will be with the first integration, and e power minus j n omega naught t dash will be with this integration. 1 extra 1 upon t is here, that's why it is multiplied by capital T outside of the bracket. If we see the formula to determine the Cn of a given signal xt, it will look like 1 upon t 0 to t x1 tau e power minus j n omega naught tau d tau. It means that this is Cn, and this is 1 upon t x2 t dash e power minus j omega naught t dash dt dash, means this is dn, and this will be multiplied by the fundamental period of the signal, means convolution of x1 t with x2 t will produce the multiplication of coefficients as t times Cn into dn, where Cn and dn are the Fourier coefficients of the signals x1t and x2t. It means that if we will take convolution of two signals, their coefficients will be multiplied with each other. This is called convolution property of the Fourier series, or it is also called convolution theorem. So there are some more properties in the way. This is all for this lecture. We will come to know some more properties in the coming lectures. Thank you.